Computing the average case runtime of an algorithm involves calculating a expected value. And in order to calculate that expectation, we need to deal with a summation, and sometimes we know summations can get messy. So we want to remember a few common summations that might be able to help us when calculating some messier summations. So let's actually take a look at a few of these. And first, let's talk about the geometric series. And the formula for the geometric series goes something like this. If you have, let's begin our index of summation from 1. And if you have something that looks like a plus a times r plus a times r to the 1, or sorry, this is r to the 1 here, a times r squared plus a times r cubed all the way down to a times r to the n minus 1. If we see something of this form, then we can say, okay, we can put it into a summation formula that looks like a times r to the n minus, or I should say I minus 1. And this is equal to, this whole thing is equal to a times 1 minus r to the n over 1 minus r. And this r is a ratio that's between -1 and 1, and strictly between -1 and 1. So the absolute value of r has to be less than 1, in other words. Right? So this is the finite geometric series formula. There's also one for an infinite geometric series. So say we have an infinite geometric series, then this time we can begin our index of summation at 0, just to make our summation look a little nicer. A to the a times r to the I equals a over 1 minus r, right? And once again, this r is between -1 and 1, right? So this is the infinite geometric series formula. And in fact, you don't even need to remember this that much. If we just take the limit as n approaches infinity, with the formula we had before of the finite geometric series, then we can kind of see this result as r to the n just goes to 0. We are just left with a times 1 minus 0, or rather a, all over 1 minus r, which is precisely this thing right here. So maybe it's less important to memorize this if you just know your limits well. Next, let's take a look at Gauss's formula. And I think the reason they call this Gauss's formula is because when Gauss was apparently when Gauss was a kid, he got in trouble with his teacher, and his teacher made him compute the sum of the first n terms, or the first n numbers, and he did it very quickly. He said this was n times n plus 1 all over 2, and so his teacher was pretty impressed. So yeah, this is called Gauss's formula. And interestingly, if you want to, if you square this, right? If you square Gauss's this summation, then that equals, we can just square this whole thing, n squared times n plus 1 squared all over 4. And it turns out that this actually equals the summation from I equals 1 to n of I cubed, right? So that's pretty neat, I think. If you sum or square this, you get this, right? That's pretty interesting. Let's actually take a look at what this looks like for I squared, right? So from I equals 1 to n, we sum I squared. So what does that look like? Well, it's not as we can't really see a pattern like we just did for the other one, but it looks like this: 2n plus 1 all over 6. So this is I squared, summing things like 1 plus 4 plus 9 plus 16 and so on. And this is what it looks like, right? All the way to n squared. Yeah, so this formula gives you that summation. And if you were in an exam, maybe if you had access to a cheat sheet, this is something you might want to remember or write down. And we can also talk about the sum of consecutive terms. So two consecutive terms being summed up from k equals 1. And this is k times k plus 1. And this equals n times n plus 1 times n plus 2 all over 3. And if we take the reciprocal of this and sum those, then this is from k equals 1 to n of 1 over k times k plus 1. And this looks like, actually it doesn't even look anything like this. It looks like n over n plus 1. Okay. So yeah, these are summing consecutive terms, or the reciprocal of consecutive terms. And that's what it looks like. Okay, so we talked about a few common formulas. Maybe there's just one more if I want to mention this. Kind of looks like the infinite geometric series, but this begins at some j. Our index of summation begins from j, and we have a to the k, and this actually equals a to the j all over 1 minus a. Right, so slightly different from the infinite geometric series, but maybe this is also useful to know. Now let's actually look at the binomial expansion formula. We have something that's like a plus b to the n. We can say that this is the sum until n from k equals 0 to n of n choose k, a to the k times b to the n minus k, right? So this is the expansion, the binomial expansion formula, and it is sometimes useful to do things like find the moment of a probability distribution, and the moment generating function of a probability distribution, in particular for the binomial distribution. After all, this is even called the binomial expansion. But that's not really related to this course, but just something to know. It is used in different problems. And let's go over some expected value stuff. So expected value is defined. So it's defined as we take the sum of all x such that this is x times probability of discrete random variable measurement equaling x, right? So this is the definition of expectation, and it has a few unique properties. First, we want to talk about the linearity of expectation. Expected value is linear. So that means we can have something like expected value of d times x plus y is equal to the expected value of y plus d times the expected value of x, right? And we can just bring this d to the outside and separate this addition to the addition of two expectations, and that is precisely why we say that expectation is linear. Now, we can also see that if we have some discrete random variable x, and we have some function g of x, then we can take the expectation of this new random variable, g of x, and this equals the summation. This almost looks identical to the definition of expectation, except that this instead of an x here, we just have a g of x multiplied by the probability that the measurement is equal to x, right? So yeah, if we have, let's say g of x was something like a times x, right? So this is just expected value of a times x, which is a times the expected value of x. And we know this because expected value is linear, and this is also equal to a times the expected value of x, px equals x, and this is also equal to ax times p of x equals x, right? And this is, again, g of x. So yeah, this is just one example, but this is a cool property of expectation as well. So let's take a look at a couple of common probability distributions. So we'll look at the geometric and the geometric distribution and the binomial distribution. So if we were, let's say we were interested in the number of trials that had to occur before the first success. So in this case, we have some random variable that represents the measurement on the number of trials that had to happen before the first success. And we say that the probability that x equals k, so in other words, the probability that the number of trials before the first success had to be k is equal to q, which is the probability of failure, the chance of failure happening k minus 1 times, and then we observe the first success. So the probability of failure to the k minus 1 times the probability of success p. And this is precisely the geometric distribution. And one thing to note is this k is a natural number, and it's greater than or equal to 1. So it's greater than or equal to 1, right? And it turns out the expectation of a geometric distribution is 1 over p. Right? So 1 over p. That's the expectation of a geometric distribution. Now let's take a look at binomial distribution. So say we had this random variable x, and this sort of measures the number of successes we observe in n trials. So over n trials, how many successes do we observe? That is what x measures. So we say probability that x equals k, where we would say we saw the probability that we observe k successes in n trials. Well, this is equal to n choose k, p to the k, so the probability of success, multiplied by the probability of failure, which is 1 minus p, to the n minus k. And you might see this written as q sometimes, but in the case of a binomial distribution, we just write 1 minus p. And the thing to note is that k is in 0, 1, 2, all the way to n. All right, and it turns out that the expected value of a binomial distribution is n times p. Right, so the number of trials you have multiplied by the probability of success is the expected value of this binomial distribution. All right, so we went over a few common distributions, and we took a look at a few common summations, and hopefully if you have the opportunity to write some of these down on a cheat sheet, I would highly encourage you to do so, because these you can't really remember unless you have them at hand, or you can't really remember very fast unless you have them at hand. So at least that's what I find. So yeah, maybe that's a good idea for you guys. So thanks for watching.